Hello, welcome to today's section. Math 1C, we're going to continue chapter 11. Chapter 11, 11.3. Very well. So what we learned so far? Let us review a little bit. We learned that we can define a new function, which we call a sequence. F of n equals to a sub n. It has some terms, a sub 1, a sub 2, a sub 3, and so on. Then we can take this sequence and define a new object, series. The sum an, n starts from 1, goes to infinity. Okay, our goal is to analyze different series, go over different techniques to see if they have a convergent or divergent series. The integral test. Very well. One of the very famous and important tests in analyzing a series is integral test. This test says, suppose, so let f as a function be continuous and also positive and decreasing function on an interval 1 to positive infinity. So 3 conditions. First of all, you have a continuous function, then it is positive, it's above x-axis, and it is decreasing. 3 conditions. It means that if you take the derivative of the function, the derivative of the function is negative. So the derivative of the function on the interval is negative. Then the series sum f of n starts from 1 to infinity is convergent if the integral of f of x dx, x ranges between 1 to infinity, is convergent. And the series sum f of n starts from 1, goes to infinity, is divergent if the integral equivalent to your series, you have an integral f of x dx, x starts from 1 to infinity, is divergent. Example. Okay. Consider the following series. Sum 1 divided by n squared plus 1, n starts from 1 and goes to infinity. Okay, as you can see, here you have a series. So this is not a geometric series. And we haven't seen this series before. So the function equivalent to this series, f of x, or the general term, is 1 over x squared plus 1 over the interval I 1 to positive infinity. If this function satisfies the 3 conditions for the integral test, then we can apply integral test. So let us check to see if f of x satisfies the three conditions of the integral test. The first condition, being continuous. Okay. Is it continuous? Of course, you have a rational function and the domain is R. It is continuous on 1 to positive infinity. I'm not talking about the left-hand side of this graph. I'm talking about the right-hand side of this graph, which is continuous with domain R, all numbers are included. B, is it positive? Of course. The denominator is positive, your numerator is positive, the fraction is positive as well. 1 is positive, x squared plus 1 also positive, so f of x is positive. It's above x-axis. The third condition, is this a decreasing function? If you don't remember the graph, don't worry, you can always take the derivative of this function and check the derivative. Decreasing. So let us take the derivative of this function. If the derivative is negative on 1 to positive infinity, you say that, hey, I have a decreasing function. So the derivative of this function, f prime of x, here you have a quotient function. The derivative of 1 is 0 times x squared plus 1 minus the derivative of your denominator is 2x times 1 divided by x squared plus 1 squared. So this is just 0. You get minus 2x divided by x squared plus 1 squared. On this interval, the derivative is always negative. So on I equals to 1 to positive infinity, the derivative is always negative. It means that you have a decreasing function. Okay, all conditions are met. Now we can use the integral test. So since all three conditions are met, we can apply integral test. Okay, let us take the integral of this function. The integral of 1 over x squared plus 1 dx, while x ranges between 1 to infinity. 1 over x squared plus 1, if you remember this integral, this is inverse tangent of x. Inverse tangent of x, x ranges between 1 to infinity. There you go. You have inverse tangent of infinity minus inverse tangent of 1. So what is inverse tangent of infinity? Remember that. Inverse tangent, if you think about it this way, you have theta equals to inverse tangent of a value. That value is equal to the tangent of that angle. But how do you define tangent? Tangent is sine divided by cosine. And you know that this A is infinity. What is the angle on 1 to positive infinity that the tangent is infinity? The denominator must be equal to 0. Cosine theta is 0 if theta is pi over 2. So substitute this question. You have pi over 2 minus inverse tangent tangent of 1, as you know, it is pi over 4. Pi over 4. With the same argument, the inverse tangent of number 1, value 1, is pi over 4. If you take common denominator between these two, you get 2 pi over 4 minus pi over 4, which is pi over 4. Since the integral is convergent, it converges to pi over 4, you say that, hey, my series is a convergent series. So this is your conclusion. Since the integral is convergent, so as our series. Let us continue. We're still on page 1. Definition of a P-series. So a P-series is defined this way. A P-series is defined as sigma n raised to an exponent like P, and starts from 1 to infinity. So 1 over infinity. Then we don't have to worry about the negative exponent. So n raised to p. You say that if p, the exponent, is greater than 1, then P series is convergent. So if P is equal to 3/2, if P is equal to 2, if P is equal to 3, and so on, you have a convergent series. If P is equal to 1, then we have a harmonic series. Then the harmonic series, as you know, is divergent. And if P is less than 1, then for sure you have divergent series. Then our series is divergent. You can prove this using integral test. Okay, let's go over some examples together, see what's going on. Example. Which one is convergent? So the first one is the series 1 over n to the third, and starts from 1, goes to infinity. And the second one is the sum 1 over n raised to a third, and starts from 1, goes to infinity. So both of these are P series. Both are P series. P in this case is 3. P is greater than 1. So we have a convergent series. You can use integral test to make sure you have a convergent series. When you're referring to P series, it means that you understood the definition. In this case, P is equal to a third, which is less than 1. So our P series is a divergent series. Okay, let us make it more interesting. We're moving on to page 2. Example. There you go. So do we have a convergent or divergent series? You have series ln of n divided by n and starts from 1, it goes to infinity. Okay. There you go. So this is not a P series. This is not a geometric series. We haven't seen this series before. Let us try to see if it fits the definition of the integral test with satisfying those function conditions. So let us check the integral test conditions. So f of x is equal to ln of x divided by x. Your interval is 1 to positive infinity. On 1 to positive infinity. First of all, is this a continuous function? Continuous? Of course it is continuous. Remember that the domain of this function, you have to take a look at your ln of x. X must be positive, and x cannot be 0. So since the domain of this function is 1 to positive infinity, we're good with the domain of this function. We're not worried about the function not being continuous. So it is a continuous function. The second one, is it a positive function? Positive? Is it above x-axis? Of course, x is positive. Your x is positive. Your denominator is positive. Your ln of x x is also a positive function. Ln of x is also above x-axis. So in general, you can say that, hey, I have a positive function. 3, do they have a decreasing function? Decreasing. To make sure you have a decreasing function, you can take the derivative of this function, and the derivative must be negative on 1 to positive infinity. So to find the derivative of this function, you can apply quotient rule. The derivative of ln is 1 over x times the denominator, which is x, minus the derivative of denominator 1 times ln of x. Divided by x squared. So the derivative of this function is equal to. If you cancel out these two, on the numerator you have 1 minus ln of x divided by x squared. Very well. Your denominator is always positive, and on 1 to positive infinity, your numerator is negative. So since your numerator is negative, the derivative of the function is going to be negative, and you have a decreasing function. So since all conditions are met, you can apply the integral test. You have the integral of ln of x divided by x. X ranges between 1 to positive infinity with respect to variable x. To find this integral, improper integral, we can use u sub. So let us use U-sum to solve this improper integral. So U is ln of x, du is 1 over x dx. So your integral is equal to integral of u dg, which is equal to a half u squared, which is equal to a half ln of x squared 1 to positive infinity. There you go. You have a half ln of infinity raised to 2 minus a half ln of 1. This is 0, and ln of infinity is infinity. So we have a divergent integral. It means that our series is divergent. So your conclusion, since our integral is divergent, our series is divergent. Let us continue. So I expect you to ask, what if I cannot apply integrals? What if I don't have a p-series? What if I don't have a geometric series? What else? So if we have a series like a sub n starts from 1 to infinity, if it's not a p-series, if it's not a geometric series, if you cannot apply, for example, integrals, next step is to take a series that we already know is convergent or divergent and compare it with this series. If none of these working, we can compare our series with a known series. We call this comparison test. So we say that suppose let series A sub n and series B sub n are both positive series. If you have this condition, if an is less than equals to bn and series A sub n starts from 1 to infinity is a divergent series, then so as series B sub n. So if the smaller series, if the smaller term gives you smaller series to be divergent, then the bigger series is divergent as well. And if series B sub n is convergent, then so as a smaller series sigma an and from 1 to positive infinity. So positive terms, an is less than equals to bn, then you can compare these two series. If the smaller series is divergent, so as the bigger series. If the bigger series is convergent, so as your smaller series. Okay, let's see some examples here. So suppose I'm giving you this crazy looking series. Example. Is the following series convergent or divergent? You have sum 5 divided by 2n squared plus 4n plus 3, and starts from 1, goes to infinity. Okay, perfect. Is this a p-series? Of course not. Is this a geometric series? Of course not. Okay, can I apply the integral of this? How would I take the integral of 5 divided by 2x squared plus 4x plus 3? So what I'm going to do, I'm going to take this term, the term, general term, which is 5 over 2n squared plus 4n plus 3. Think about it this way. You have 5 divided by, for example, 2 plus 4 plus 3. This guy is less than 5 divided by 2. That makes sense. When you increase the denominator, you get a smaller fraction. So this fraction is always less than 5 divided by 2. So this general term is less than 5 divided by 2n squared. Okay, take a look at this general term. Here you have a p-series. So if you form series 5 over 2n squared and starts from 1 to infinity, you can write 5 over 2 in front of the series because it's just a number, it's just a coefficient. 1 over n squared, and starts from 1 to infinity. Very well. Here's my eraser. So as you can see, your series 5 over 2n squared plus 4n plus 3 is less than 5 over 2 series 1 over n squared, 1 to infinity, and starts from 1 to infinity. Both of them are positive, and the first series is less than the second series. You already know that this is a p-series. P-series, p is 2 greater than 1. So since the bigger series is a convergent series, your smaller series also convergent. Is a convergent series. So by comparison, test our series is convergent. Let us continue. We are on page 3. You can also find the limit of the quotient of two general terms. So it's like this. the limit comparison test. Let two series be positive. Have positive terms. Take the limit of an divided by bn while n goes to infinity. If this limit is equal to a constant like c, and c is a number greater than 0, and c is a number. Guys, I'm not talking about infinity. I'm talking about c to be a number and be a positive number. Then both of these series are convergent or both of them are divergent. Then both series an and series bn are convergent or both are divergent. Let us go over one example to see what's going on. Example. Suppose you have this series. 1 over 2 to the n minus 1, n starts from 1, goes to infinity. Okay. What is this series? It's similar to a geometric series, but I have minus 1 on the denominator. So it is not a geometric series. So let us work with a convergent geometric series. Sum 1 over 2 to the n, n starts from 1 to infinity. We already know the behavior of this series. R, or the ratio is a half, R is between -1 and 1, and we know that this is convergent. Okay, let us use the limit comparison test. The limit of, suppose this is on the numerator, 1 over 2 to the n minus 1 divided by 1 over 2 to the n, while n goes to infinity. We're getting back to calc 1. This is the limit of 2 to the n divided by 2 to the n minus 1, while n goes to infinity. Both of these terms are going to infinity with the same speed, so you can cancel out these two and you get 1. This is your c. C is a number, c is greater than 0. And since you already know that your geometric series is convergent, the conclusion is your series is convergent. Since the geometric series is convergent, so as our series. So if you don't feel comfortable with intuition here, you can apply L'Hopital's rule. L'Hopital's rule say, hey, I have infinity over infinity, so this is the limit of the derivative of numerator is 2 to the n, ln of 2, divided by the derivative of denominator is 2 to the n, ln of 2, and the derivative of negative 1 is 0, so I can cancel out all of these terms, which is equal to.
Professor?
Let's see what else do we have. Okay, another example for you. We're still on page 3. So suppose you have this series example. You have series 2n squared plus 3n divided by, I have square root of 5 plus n squared, n starts from 1, and it goes to infinity. Okay, perfect. Let's see what do we have here. Two n squared plus 3n divided by square root of 5 plus n squared. As you can see, this is not a p-series. This is not a geometric series. How do we use integral test? So let's see if we can actually compare this series with a different series, or we can apply limit comparison test. So comparison test. Oh, sorry, this is fine. There we go. So your term with the largest exponent is 2n squared. I'm trying to form a new series that I can actually use and compare it with that series. So let us take the terms with largest exponents from the numerator, from the denominator. Between 2n squared and 3n, of course, this has lower exponents. So on the numerator, I'm going to take 2n squared divided by. On the denominator, if I forget about 5 as a constant, I get square root of n to the 5th. I'm going to simplify this as much as I can. I get 2n squared divided by, this guy is n 5 over 2, which is equal to 2 divided by n raised to 5 halves minus 2. This is equal to 2 divided by n raised to 5 halves minus 2 over 2, which gives me, so this is 4 over 2, which gives me 2 divided by n raised to a half. I have a p-series, p is a half, less than 1, so it's a divergent series. So this is a p-series, p is equal to a half, less than 1. I have a divergent series. Divergent series. So now I'm going to use limit test. Now use limit test. The limit of your general term, 2n squared plus 3n divided by square root of 5 plus n to the 5th divided by 2 over n to a half while n goes to infinity. So what I did, I took the largest term on the numerator, the largest term on the denominator, I simplified it as much as I can, and I formed a series that I already know if it's convergent or divergent. Now I'm going to move on to use the limit test. We are now just using the techniques that we learned in Calc 1. This is equal to the limit. So I'm going to multiply the numerator and the last denominator. I get square root of n times 2n squared plus 3n divided by 2 times square root of 5 plus n to the 5th, and I'm going to send n to infinity. Okay. So intuitively, since n goes to infinity, we're actually working with terms with the largest exponents. This is equivalent to limit of square root of n times 2n squared divided by 2 times square root of n to the 5th. N goes to infinity. Okay, so I have 2 and 2, we can cancel out 2 and 2. I have n raised to a half, n raised to 2 divided by n to 5 over 2, and I'm taking the limit while n goes to infinity. This limit is equal to 1. Your c is 1. Your c is 1, which is a constant greater than 0. It means that if one of the series is divergent, so as the other one. Since our P series is a divergent series, your series is divergent as well. So we have a divergent series. Okay, alternating series. So this is page 4. Alternating series is defined this way. Series -1 raised to n minus 1 times bn, and stops from 1 to infinity. Okay, if bn is decreasing, so if bn is decreasing, and if the limit of bn while n goes to infinity is equal to 0, then you can conclude that the series is convergent. Alternating series. One example for you. Example. Suppose you have series -1 raised to n minus 1 divided by n stops from 1 and goes to infinity. Okay, this guy can be written as series -1 raised to n minus 1 times 1 over n stops from 1 and goes to infinity. So as you can see, your bn is equal to 1 over n. The first condition, bn must be decreasing. bn 1 over n is decreasing. Why is that? If you take the derivative of 1 over n, the derivative of 1 over n, it is the derivative of 1, 0 times n, which is 0, minus the derivative of n, which is 1 times 1, -1, divided by n squared. N squared is always positive, your numerator is negative, so the derivative is negative. So bn is decreasing. The limit of bn while n goes to infinity is 0. Why is that? Of course, you already know that limit of 1 over n while n goes to infinity is 1 over infinity or 0. So it satisfies the condition of alternating series, so your series is convergent. convergent. So this is your conclusion. Since it satisfies the condition of alternating series, it is convergent. Okay, let's define absolutely convergent series. So absolutely convergent series. So absolutely, it's coming from absolute value. A series like sigma an and starts from 1 to infinity is absolutely convergent. It's absolutely convergent if its absolute value and starts from 1 to infinity is convergent. So we are taking the absolute value of the general term. Absolute value. Let me write an M here for you. A sum for example, is the series -1 raised to n minus 1 over n squared and starts from 1 to infinity. Absolutely convergent. Okay, let us take the absolute value of the general term. The sum, absolute value of -1 raised to n minus 1 divided by n squared. So since you have -1, the absolute value of -1 is always positive 1. This is equal to the sum 1 over n squared. N squared is already positive, so you can get rid of absolute value. N starts from 1 to infinity. We know that this is a P series, and P is 2 greater than 1. So of course this series is convergent. So the answer is yes. This series is absolutely convergent. So we have it here. If a series is absolutely convergent, then you can conclude that the series is convergent itself. Then it is convergent. So, question I expect you to ask, if a series is convergent, then can we conclude that it is absolutely convergent? We have a convergent series. Can you conclude that it is absolutely convergent? Think about this series. Alternating series, -1 raised to n minus 1 divided by n. N starts from 1 to infinity. This alternating series is convergent, for sure. You don't have any problem with the series itself. What if I take the absolute value? The absolute value is 1 over n. N starts from 1 to infinity, which is a harmonic series, and it is a divergent series. So the answer is okay. 2 more tests for you: ratio test and root test. Page 5 and 6. So let me write this here for you, then we go over example. The ratio test and the root test. So these tests are defined this way. If the limit of absolute value of an plus 1 over an while n goes to infinity is equal to L, and L is just a constant, and L is less than 1, then you say that, hey, my series is absolutely convergent. Then series an is absolutely convergent. If L is greater than 1, then your series is divergent. Is divergent. And if L is equal to 1, we cannot use this test. Now ratio, and then root test. For root test, you take the nth root of your general term. So if the limit of the nth root of absolute value of an while n goes to infinity is equal to L less than 1, then the series is absolutely convergent. It's absolutely convergent. The same argument. If L is greater than 1, it is divergent. And if L is equal to 1, we cannot use this test. two examples for you. Example. Consider series -1 to the n cubed divided by 3 to the n, and starts from 1 and goes to infinity. Let's apply a ratio test here. The limit of, ratio test. The limit of absolute value of an plus 1. So I have -1 raised to n plus 1, 3 raised to n plus 1, divided by 3 to n plus 1. Everything is divided by a sub n, -1 to the n, 3 to the n, n to the third, n plus 1 to the third, and here you have n to the third, divided by 3 to the n, while n goes to infinity. Since you have absolute value, you can just ignore the -1, because absolute value of -1 is just positive. We don't care about the exponent. So this is equal to the limit of absolute value of n plus 1 to the third divided by 3 to the n times 3 divided by n to the third divided by 3 to the n, while n goes to infinity. Let us simplify this fraction. Here you have limit of absolute value. We multiply 3 to the n by n plus 1 to the third divided by, now you multiply 3 to the n times 3 by n cubed, while n goes to infinity. So of course you can cancel out 3 to the n, 3 to the n. You have the limit of absolute value of n plus 1 to the third divided by 3 times n cubed, while n goes to infinity. Intuitively, n plus 1 to the third and n to the third, they go to infinity at the same speed. So you can cancel out these two. You're left with a third. So 1 over 3 is your L. This is less than 1. So you have an absolutely convergent series. Since L is less than 1, we have an absolutely convergent series. So, since your series is absolutely convergent, with previous theorem, you can say that, hey, I have a convergent series. So let me write this here for you. And goes to infinity. So L is a third less than 1. So since L is less than 1, we have the absolutely convergent series. And by previous theorem says our series is convergent. Next example for you. this example. Suppose you have series n to the n divided by n factorial and starts from 1 and goes to infinity. Okay, let's apply ratio test, see what do we have here. Ratio test. So here you have the limit of absolute value of n plus 1 raised to n plus 1 divided by n plus 1 factorial over n to the n over n factorial and goes to infinity. Remember that n factorial is n times n minus 1 times 2 times 1, and n plus 1 factorial is n plus 1 times n factorial. Okay, first of all, let's multiply these two, we get the limit of absolute value of n factorial, n plus 1 raised to n plus 1, divided by n plus 1 factorial, n to the n, and goes to infinity. Let's simplify this side. We have the limit of absolute value of n factorial, n plus 1 raised to n plus 1, divided by n plus 1 times n factorial, n to the n. And let's put everything in absolute value, n goes to infinity. Of course, you can cancel out n factorial and n factorial. So now you will have a limit of absolute value of n plus 1 raised to n times n plus 1, divided by n plus 1 times n to the n, and goes to infinity. Very well, let us get rid of n plus 1 and n plus 1. What's left? We have the limit of n plus 1 to the n over n to the n, while n goes to infinity. So let us get back to Calc 1. This is the limit of n plus 1 over n raised to the n. Since n is greater than 1, we can get rid of your absolute value. N goes to infinity, which is the limit of 1 plus 1 over n to the n, while n goes to infinity. And if you remember the definition of Napier number, this is equal to E. Of course, E 2 point something, your L is greater than 1. Greater than 1. So we have a divergent series. Okay, another example. Let us see how we apply root test. So suppose you have this series 2n plus 3 divided by, let's put everything inside parentheses, divided by 3n plus 2, everything is raised to exponent, n starts from 1 to infinity. Okay. So since you have exponent n, instead of using a ratio test, it's better to use root test because of this exponent n. Because if I take the nth root, I can get rid of exponent n. So let us apply root test, see if we can use root test in this case. Root test says I take the limit of the nth root of 2n plus 3 divided by 3n plus 2. I just put everything inside absolute value, and here I have n, while n goes to infinity. infinity. Very well. The index and the exponent are the same, so I can get rid of my radical. I left with the limit of absolute value of 2n plus 3 divided by 3n plus 2, while n goes to infinity. So of course n is positive, I can just get rid of the absolute value sign. Because I have infinity over infinity, I can apply L'Hopital's rule. I get 2 divided by 3, 2 thirds. This is my L. L is 2/3, and as you can see, L is less than 1. It means that my series is absolutely convergent. By using the theorem, your series is a convergent series. Since L is less than 1, so we have an absolutely convergent series, so it is convergent.